Hey, what's up everyone? Jason Turley here, back with another video. We're once again looking at ROP Emporium. I know it's been a while, but we're going to continue on in the series, learn about a technique called return-oriented programming, which you would utilize this technique if your binary that you found a buffer overflow exploit for example, has something called the non-executable bit set, or it has data execution prevention set, which is also known as. So if you're not able to execute shellcode on the stack, you would use a technique like the one we'll show today throughout this series, and you will get your shellcode execution. In the case of these challenges, we're not always executing shellcode and getting like a shell on the system, but we are solving these challenges in increasingly difficult order. If I go to the main page of ROP Emporium, we did knock out return to win and split before. Now we got challenge 3, call me, but we will go over all of these eventually. So let's read the description for call me. Reliably make consecutive calls to imported functions. Use some new techniques and learn about the procedure linkage table. And you can download your binary here. We're going to do x86-64. But feel free to do any other architecture that you want to play with. So it reads, failure is not an option. How do you make consecutive calls to a function from your ROP chain that won't crash afterwards? If you keep using the call instructions already present in the binary, your chain will eventually fail, especially if you're exploiting a 32-bit binary. And then it asks you to pause and reflect to consider why this might be the case. And then there's some notes here about the procedure linkage table that stores different functions and function calls and addresses for the library code you'll use in the C library. And they have a nice write-up here on what it is, but we're not going to go over that in too much detail in this video. We're just going to solve the challenge and then point out anything that I think might be relevant as we do it. So what is the goal? You must call these three functions, call me 1, 2, and call me 3, in this order, each with the arguments ox deadbeef, cafe babe, dude food, and then it gives an example. So we're just calling three functions and we're passing three arguments to those functions. And then it notes here, hey, if you're using the x86 64-bit binary, you need to double those values. So instead of just deadbeef, it'll be deadbeef twice, or cafe babe twice. And that's simply because ox deadbeef or ox cafe babe, those are 32-bit values or 4-byte values. And on x64, these we want to use the, I guess, full address space for whatever reason. So we'll be using the full 8-byte value. The solution here is simple enough. Use your knowledge about what resides in the procedural linkage table to call the call me functions in that order. Okay. And there's also an alternate solution, so that could be interesting. And I have solved this challenge previously. If we look at the date, it was July 1st, and I wrote up a blog post on it. It has been a while, but if you would rather look at this in the context of a blog or something where you can copy and paste or quickly scroll through instead of a video, feel free to help yourself here. I do have some of the write-ups available on my website, but I want to make a standalone video for this as well. So with all that preamble out of the way, let's come here. You see I already have my ROP Emporium directory. Let's create a directory called call me, and let's actually change directories into it. And now we can download that binary that we took from the website. I accidentally added a little tilde at the end. Let's delete that. We see it's 100% downloaded and it's saved in something called callme.zip. So let's unzip that. And we no longer need that callme.zip file. But we see it did give us a few files. Callme, libcallme.so, and then these key files. That's interesting. So let's run file star just to see what we're working with here. Make sure that's nice and big so everyone in the back can see it. So callme is a 64-bit executable, so we already knew that. It's dynamically linked, meaning that all the libraries it needs, all the additional code, it's not contained within the binary itself. It's stored somewhere else on the system that the binary will have to pull from. And that's likely what this .so is. SO just means shared object. It's just additional code, utilities that your binary might pull from. In Windows, these are called DLLs, so anything that has .dll. In Linux, they end with .so. Not that file extensions really matter in Linux anyway. And since we have it pulled up, we can see here, yeah, it's a shared object. It's also 64-bit, dynamically linked, and we get the hash. It's not stripped. Neither of these are stripped. And that just means they do have the symbol information. So if you're opening this up in a debugger or a disassembler, we will actually see functions like callme3 and callme1, and we'll actually see that. And if the binary is stripped and you open it up in something like Ghidra, it might just say like fun, F-U-N _ and then some random numbers, or like sub for like subroutine. It makes it a little bit more challenging and tedious to reverse engineer and understand, because all that helpful information, all that context is like stripped away. And then we have these encrypted data files, or one encrypted data file, like encrypted flag, and then two things that are just listed as data. So that's not too helpful. If I try to cat out that encrypted flag, we see it's garbage. It doesn't really work. It doesn't really print out a flag or anything like that. So while we're here, we can do LDD on callme. LDD is a cool command. It just shows what libraries your binary is using. So it's using some Linux stuff. We can see the address for that as well. And we do see libcallme.so. So our binary callme is using this shared library. I don't know if that will be relevant later, but it's just something to take note of. Let's do robin2 tag z just to look at the strings of callme. Actually, before we do that, before we get too ahead of ourselves, do I have checksec installed? I do. Let's check out the security of this. It did not like that for some reason. Pwn checksec. Yeah, I don't know why checksec is crapping out on me. But let's just do robin2 tech capital I. So if you do have Radare 2 installed, which is like a suite of tools for reverse engineering and disassembling, you do get a function of tools, and one of them is robin2, and I did tac capital I or hyphen capital I, however you like to pronounce it, and it will just tell us more information about this binary. We get the base address. But what we really care about is the security protections down here. We see NX is set to true, so it is non-executable. So if we really wanted to put our shellcode on the stack and execute it like that, we cannot. And we knew that because that's the whole point of these challenges. And it doesn't really have address space layout randomization or anything like that enabled. It's not stripped, and it is using virtual addressing. So now let's actually look at the strings. I've started to like using robin2 tag z instead of the regular strings command. If I do the regular strings command, it's going to give me a lot of output, and it is helpful. It's tried and true. We can see the names of the functions here. It's just a lot of garbage. I shouldn't say garbage. Just the way it is laid out isn't always the most helpful. But we do see something called useful function in pwnme. We see a temp file that's getting created. Useful gadgets. So these are probably all functions that we'd want to examine in either object dump or GDB. However, I do like robin2 with the tag z flag because it does print out strings, but it just gives you some of the more useful ones, I guess. And it also gives the address of where they live in the binary, which is really helpful for doing return-oriented programming, as we'll soon see. So unfortunately, the strings here aren't too helpful, right? It's just telling us, I guess, this banner, this ASCII text that would get printed out. If I run callme, we see this is exactly the same. So we know this song and dance. We have to enter something. I'm just going to say, please subscribe. And nothing really happened. Let's look at the strings of that shared object. Okay, so we see callme1 getting called correctly, callme2 getting called correctly. So these are probably checks that will happen once we pass that win condition, the win condition of doing callme1 and specifying the 3 arguments. Interesting. So when I ran strings earlier, we did see useful function and useful gadgets. Let's inspect that a little bit more. We can do object dump or we can do GDB. Either one is fine. I'm gonna do tag M to specify Intel syntax, and let's pipe that into less. Now I'm gonna search for callme underscore. Okay, so we see callme 3. We get the address of that. Doesn't really do much. It pushes the value 2 onto the stack, and then it jumps to this address in the procedural linkage table. Let me see if I can search for useful. So useful function. Okay. Okay, so useful function, it just calls these three functions, the three functions that we'll need. So I think it's just there so we can get the address. We can ignore what's being put in these registers. So it's setting up. So in x64, when you call a function, you're going to pass the argument to that function inside of the registers available to you. So RDI or EDI, ESI, and EDX are the three registers you'll pass it to in order. And we see that being done here. So this is calling callme3 with a value 4, 5, and 6. I guess it's true for all of these. All of these functions are being called with values 4, 5, and 6. So what this looks like, so they're just doing this, callme1, value 4, 5, 6, and that's just the same for all of these, right? Callme1, 2, and 3, and we want to change those to be OX dead beef and whatnot. But I think you guys get the point. I think I'm rambling on a little too much. Let's actually open this up in GDB and let's start getting our exploit going. GDB on callme. And you see by my prompt, I do have GDB enhanced framework installed, so it will make disassembling this just a little bit easier. We can run the binary and be like, please sub, and it does exit. So let's see if we can cause some type of buffer overflow. So I'm gonna do pattern create 100 to get a unique set of 100 bytes. And now when I rerun the program, let's slam that in there. And we do see, we cause some type of crash to happen. So if we scroll up a little bit and we look at the contents of what's in our registers, we can see that the base pointer is completely overwritten. And we see the stack pointer points to the rest of our junk. If you watch the other videos, this should all look very familiar. Our return address is not overwritten, and that's okay, but we still caused a segmentation fault. So we need to find the address of how, we need to figure out how many bytes it takes to fill our buffer, overwrite the base pointer, and then get to the stack, or the return address rather. So we can easily do that with a pattern search $RSP to search for the stack pointer. And we see it takes 40 bytes of junk to overwrite our return address. So how do we want to showcase this? Let me just do something quick in Python. Let's print out 40 A's. And let's print out 40 B's as well. I'll do it like this, B times 8, and then C times 8, and D times 8. And this will make sense in 1 second. See if that works. Forgot the closing quote. Let's grab this, rerun the program, slam in this mess we just made. So hopefully this helps illustrate it a little bit better. We can see, let's examine 24 gigs as hex from the stack. So we can see our 40 A's being printed on the stack. Let's actually run it like this. Okay, so we can see our 40 A's being printed to the stack. We see the base pointer is overwritten here. The base pointer is now, should be all our B's. No. So we did 32 bytes to fill the buffer. And then the base pointer is 8 bytes. And now the stack pointer, which is at this address that ends in DCF8, Let's find that. DCF8, that's where our B's are. So that's where our return address will point to. And then we see our C's and our D's. So this is where we're going to start wanting to add our ROP gadgets, and that's where we're going to start wanting to add addresses for the other functions. So we control the instruction pointer. So knowing that we can overwrite the return address, we want to overwrite it with the address of something else. So we saw something called useful function. Let's look at that again. Useful function. And let's also disassemble useful gadget, because we saw that in our string output as well. So awesome. So useful gadgets, it just sets up the 3 arguments, RDI, RSI, and RDX. So we might want to take note of this address for later, 40093C. And a useful function, I don't think we'll actually need this. We might just want to steal these addresses here. Just steal these calls to callme 1, 2, and 3. I don't think we actually need the address of useful function, if I'm understanding it correctly. So let's see if we can draw what we want to do. That'll help me and hopefully you guys, the viewers, as well. That's not what I want. Let's make this, come on now. Let's make a nice box, something like that. And this will be our stack. And let's see if we can start drawing some of this out. I know these lines look horrible, but hopefully this will help illustrate what we want to do. So over here we have our buffer, BUF, and we know that this is 32 bytes long, so that's just a 32. And then we have our base pointer here. We know that this is 8 bytes, and then we have our return address, so where we want the program to continue execution from, and that's denoted by the RIP register. And now we just have the rest of this stack, right? And that's going to contain anything else in that buffer. So we saw before, where was it? We saw before we can control the values that get written to the stack, right? We can control all this junk that gets placed here. So instead of having that be junk, we want to fill it with something else. And what is that something else? So our buffer, we just want to overflow it. We can just throw a bunch of A's in it. So 32 plus 8 is 40. So we want 40 A's. And then we want our return address to point to something. We want it, what is our goal again? We want to do callme 1. Our end goal is to have the address of callme 1. I'll just do this, callme. This looks horrible, oh my God. Callme 1. I know that looks like garbage, but just bear with me. So we want the address of that right here. And before we call callme 1, we need the variables. We need the arguments. We need them to be on the stack for this. So we want OX deadbeef. I'm not going to write all that out. I'll just probably say arg1. This looks so bad. arg1 and arg2 and then argument 3. So this is the dead beef and the cafe babe and the dude food. And all of these are going to be 8 bytes in size. So 8 times 3, so that's 24 bytes on the stack. And then we need the address of callme 1 that we can get later. And so our instruction pointer, what we want the return address to be overwritten with is those ROP gadgets that we saw earlier. We want it to be overwritten with these, I think it was just called useful gadgets. Yeah, we want this address. We want the start of useful gadgets. And that will take the next 3 values on the stack, because that's what pop does. Whatever is currently on the stack, take it off and store it in this register. So if we put the 3 arguments, dead beef, cafe babe, and dude food, I think it was, if we put those 3 on the stack, and then we do this sequence of pops, all 3 of those will be cleared off the stack and then stored in the registers, and then we'll do the address of callme 1, so whatever that is. Cool. Hopefully that made sense. We're not going to worry about callme2 or callme3 yet. Let's just see if we can get it working for callme1. So let's make our little exploit. Let's call it exploit1 or exploit.py. User bin env python 3. We need some libraries here. So from pwn import all. We need the address of useful gadgets, and we need the address of callme1. We'll grab those in a second. We can start making our payload. We're going to do 40 A's to overwrite the fill our buffer and the base pointer. And now we want the payload to equal, we want that address of useful gadgets that we haven't defined yet. And now we need the 3 arguments. So 3 args to callme1. Let's just grab those from the binary or from the description. So dead beef. Argument 2 will be cafe babe. I'm just going to copy and paste this to save a little bit of time. And then arg3 will be dude food. Sweet. So let's fill these out. Payload plus equals arg1. Let's copy and paste that twice. So that's what our stack should look like so far. And now we need to add the address of callme1. There we go. And we can, I like adding comments to my stuff, but this is optional. OX cafe babe, and OX dude food. We need to start defining some of these addresses. So let's grab the address of useful gadgets. And just leaving the hex value like this will not work. We need to actually wrap these in a module called P64 to make them compatible with the rest of the bytes that we're sending to the function. So disassemble, what are we looking for? Callme1. Let's do object dump. Can't spell for anything. And grep callme. There we go. Callme3, callme1. There's the address. So this would be P64 as well. And these are small enough, we could do them by hand if we really wanted to convert them like that. But I don't want to. Okay, we'll have to do the same for this. Let's see if I can be fancy with some Vim recording. So insert P64 here. B 2 at Q. There we go. A little bit of Vim foo never hurt anyone. So let's review this before we run it. So starting from the top, we're importing a library, or we're importing everything rather, from Pwn Tools, which is a very useful capture the flag and exploit writing framework. And that's what's giving us access to P64, which is just a wrapper for struct.packed. So these is going to make it a nice compatible 64-bit value. So we have the address of useful gadgets. We have the address of the callme function. We have our 3 arguments that will be put on the stack. So our payload begins with 40 bytes of A's just to fill the buffer and the base pointer. Now the return address should be overwritten with the address of useful gadgets. So now the execution, it'll leave that whatever function it's in, the callme function that it's in, and it'll go to the useful gadgets function. And all that's going to do is, I have no idea what I pushed. And all this is going to do is call pop RDI, pop RSI, pop RDX, and then return. And then it should actually call the callme1 function. So let's do p.sendLine payload. I don't think we'll have to read anything yet before we send a line. And then p.receive all. Let's see if that works. So we saved our exploit. Oh, I never defined what p is. P equals gdb.attach. And this is a cool thing about using pwn tools. Save and exit. Now let's run our exploit. And this should open up a GDB window. Okay, it's not attach, it's debug. gdb.debug. Sweet. So it opened it up in a new terminal, and we do get some type of error. It says broken pipe, no such file or directory. Interesting. So let's quit out of here. Payload is not defined. I spelled it wrong. Okay. You can tell I haven't made any videos in a bit. I'm pretty sloppy and pretty slow, but that's okay. Is that the name of our binary? It is callme, right? ls callme. Yeah, I don't know why it's giving me issues. All right, let's save and exit. Let's run this again. There we go. So you can see it opened it up in GDB, nice and pretty. It hasn't run the code yet, so let's set a breakpoint. Or first, let's disassemble pwnme. That's the vulnerable function that we're looking at. We can see our buffer being allocated here. It's retracting OX20, which is 32 bytes. So it's allocating space for that buffer. It's calling memset with a value of 0. So it's zeroing out our buffer because memory in C is not guaranteed to be unallocated. You never know what's in a buffer when you allocate it. So it's nice just to clear it out and make sure it's empty. It's printing out this value, put string. So what is that? So it prints, hope you read the instructions, and then it's going to print this as well. What is this string? Okay, so this is a little prompt. And now it calls read. So here's the actual vulnerability. Our buffer is 32 bytes in size, but it's reading up to OX200. So what is that? Examine decimal, or can I just do print? Is there print? Printf? I don't remember how to use GDB. Yeah, whatever. Let's just do it in Python. OX200, it's 512. So it's reading in 512 bytes, which is a lot more than 32. So that's where the buffer overflow is. So we can throw up to 512 bytes at this thing. So let's set a breakpoint. Let's set a breakpoint on that call to read. Break star and that address. And now let's continue the program. So if we look at the stack now, it's all empty. It's all 0. There's 32 bytes of zeros. So this is our buffer, right? This is the thing that was allocated. And we can see we're about to call the read function. If I do an ni to step forward one instruction, we can see that now the stack is being overwritten. We have our A's, the base pointer is overwritten as well. And we can confirm that up here. All that is overwritten with the junk bogus A's that we sent. And now our return address, our instruction pointer, is 408E5. Or at least it will be soon. Yeah, so our instruction pointer has not yet been overwritten. So because we have not returned from the program yet. If you see here, these are the instructions that will be executed. So if we hit NI again, there's a no operation, a leave, and a return address. So let's keep stepping. Step one more. And now, since we did that, we can see where we're currently at. The top of the stack points to the useful gadgets function, and we can see that pop RDI will be called. So our return address is not yet overwritten. Let's step forward one more. And now it is. You can see the return address RIP, and it has this arrow pointing to useful functions, and we can see the next 3 instructions that will be executed. So whatever is currently on the top of the stack, it'll take it off and it'll place it in the register RDI. So let's see that in action. We see the top of the stack contains dead beef. And if we look at RDI, it has this random address. And if we dereference it, it's 0. So RDI is 0. So if I step forward one more instruction, that pop RDI occurred. Now the top of the stack is OX Cafe Babe. If I scroll up and we look at RDI, it is dead beef. So that's what we're doing. That's what return-oriented programming can offer you. Now we got fortunate that there was a useful gadget function that had the 3 exact instructions we needed, the 3 pops into the correct registers we needed. If this were not the case, we can use other tools like ROP, or even just Pwn Tools itself has utilities to do this. But we'd want to find our own return-oriented programming gadgets. But hey, if they have it here in the binary for us, why not use it? So I can keep hitting NI. I'll do it one more time. So the 2 pops occurred. We can see they're gone from our stack. You can see that those values are placed in these registers. So now we're going to return again. And we should see our call to callme, right? We should do callme. So we can see here, it looks like we're inside that callme1 function. Let's just hit NI and step forward. We're going to jump to this address. Let me copy that and do examine, let's say 12 instructions from this address. So it's going to do some printing out some information, and then it'll go to callme3. A little confusing. Let me just hit C to continue. Cannot disassemble from program counter. So I think I made an error somewhere. This is not a valid address. We see OA at the end, which is the new line character. So maybe I'm not sending something correctly. We don't want our instruction pointer to point to this. This is garbage. We want our instruction pointer to point to the callme1 function. Can I disassemble that here? Interesting. So let's exit out of this and let's open up our exploit because we have some stuff we want to change around. Let's see. Let's throw this not in GDB, but let's actually run it against the challenge binary and see what happens. Okay, when I run it against the challenge binary, we can see that callme1 was called correctly. And we see that this was a byte object. Let's open it up. This Pwn Tools version 3, or the one with Python 3, it does everything with bytes, not necessarily strings. So let's see if we can make that a little bit prettier. There we go. So callme1 was called correctly. Perhaps I overlooked something in GDB. I don't know why it was all ugly like that. Maybe I just missed this printout. Because I'm assuming it's still crashing. Sudo demessage, and then just pipe that into tail. Yeah, so we are still causing a seg fault, right? We do see the segmentation fault on callme. Let me make that even easier to read. Tail grep callme. So we see that we did cause segmentation faults, and there's that address again. So even though we're successfully completing the challenge, the code is not exiting cleanly. The return address is being overwritten. I think this is the new line that we sent, 0A. But for the sake of the challenge, we don't really care too much. We could find an address for like an exit system call and maybe allow it to like exit gracefully. But for now, we know this works. So now all we have to do is repeat the same process 2 more times for callme2 and callme3. So we want to find those addresses. Let's do object dump. And callme and grep for callme underscore. Sweet. So we have those here. So I'm going to grab the address for callme2. And let's just make it its own function or its own variable. So callme2. Slam that in there. Need to add the 0x in front. And we can do the same for callme3. And that's 6f0. So 6f0. Let's change this. Callme3. And now the process should be the same. It's going to be the same exact arguments. So we don't need to change any of this. What do we need to add? What do we need to repeat? We need to push the arguments on the stack again, right? Let me change up this comment. Yeah, I'll leave the comment as it is. Okay, so the only things we really need to grab and change is this right here. So that worked for callme1. Let's copy and paste it one more time, and let's change this to callme2. These are just the comments. These don't really matter, but just for easier readability, we'll do it like that. And before we do callme3, let's just save and exit. Save, oops, W. Python 3 exploit. Callme1 was called correctly, but not callme2. Why? Why was it not called correctly? What are we missing? So after callme1, we add our 3 arguments to the stack. Oh, I didn't do the ROP gadgets. That's what we need. Here, I can make this neater. Let me add comments. Overflow buffer, 32 bytes. So overflow buffer and base pointer. So we need that, the ROP gadget, because everything's being passed to the stack, but we need to put it in the arguments. Perfect. Let's repeat the same thing. I'm just going to highlight and grab this, yank it, and then paste it again for callme3. So change that to 3. That should stay the same. Callme3 and callme3. Sweet. So callme3 must have like decrypted the flag or something, because this prints out callme1 and 2 were called correctly, and this one just prints out the flag. So if I disassemble callme3, do I still have it in GDB? Yeah, disassemble callme3. It must actually be opening up those encrypted files. So I do see a call to fopen. So maybe it's opening up that encrypted underscore flag .dat file, and then it's doing its magic to unencrypt it. So we're not really going to reverse engineer it in this video. I think we've gone on a little bit long enough, but that's how you solve that challenge. If I look at dmessage again, let's grab callme. We see it's still segfaulting though. So we're still doing a buffer overflow. I'm curious if we add like an exit system call at the end, would it like exit gracefully? So that's it for the challenge, but just out of curiosity, I kind of want to find an exit system call and do that. Let's see if we can find one. So here's a call to exit. The big address. YOLO, let's just grab it and throw it in our exploit and see what happens. Exit call. Payload plus equals p64 of this address. And let's see what happens. Do we break anything? So it still worked. Let's do that sudo dmessage. Yeah, it did not segfault. 4278, 4278. So that was the one from before. That was the previous process. So yeah, cool. We made it exit. If I run the exploit one more time, and I do echo $? It exits cleanly. Nice. But if I open up our exploit and I take this out, what is the return code? Echo $? Yeah. So it still exits cleanly either way. That's interesting. Maybe I'm not doing it correctly, or I don't know, because it's not segfaulting anymore, right? These are all the previous processes. It's not what we're currently doing. So that's really it for this video. Hopefully it made sense. Hopefully it was informative. It was kind of nice to get back in the swing. I know I've been out for a little bit. I haven't made videos in a while, but this was fun. If you'd rather read this as a blog and not hear me ramble and talk, feel free to check that out here. I have a link in the description. Let me know in the comments below if you found this kind of stuff helpful, or if you want to see more videos like this in the future. If you want to wear like cool hacker shirts like this, the link is also in the description. And then as always, guys, take it easy and see you in the next video.